Every year, there's a handful of top tier AI conferences, and one of them is called Computer Vision and Pattern Recognition, CVPR, which is where the world's leading AI scientists in computer vision come together and compete vigorously to get published, and with new state-of-the-art algorithms and techniques for computer vision. I can't emphasize enough how difficult it is to get published in this venue, a peer-reviewed scientific venue like this. It's even more difficult to get invited to give an oral spotlight, to be one of the presenters at the conference. And it's even much harder to be a finalist for a Best Paper Award in this venue. But that's what Tzofi Klinghoffer and his team here achieved in CVPR. And we want to invite Tzofi to share that work with you today.
Thanks, Mark. Every year, there are 1.7 million fender benders in the US alone. Shown here is a recent incident from right here in Boston. And while luckily no one was injured, and this was a fairly minor incident, it's easy to imagine how deadly these events could be. And even if these cars had been equipped with the latest and greatest autonomous driving and artificial intelligence technology, that still might not have been enough to make a difference. That's because today's AI can only reason about what's directly visible to it. There's no solution on the market that allows your car to see beyond the car in front of it to enable early braking and prevent collisions like the one I showed. My name is Tzofi Klinghoffer, and my PhD research here at MIT focuses on creating superhuman visual intelligence, and more specifically, the ability to see hidden objects. So what if AI could see hidden objects? Not only could your car see collisions up ahead, but also warehouse robots could more quickly navigate to objects of interest. And for security, entire physical spaces could be mapped and monitored without expensive systems that require multiple cameras. In our lab here at MIT, we've achieved results that show a promise for this future. Let's consider a simpler example. Given a single vantage point of this chair, it's difficult to determine what might be inside it. It could be empty, or maybe there's something in it. Answering this question is really challenging because, of course, the front of the chair is occluded by its back side. Here at MIT, we've developed methods that enable complete 3D scene geometry, including the hidden bunny in this case, to be extracted from just a single view. The key to our method is to combine machine learning with emerging LiDAR technology, rather than relying on traditional RGB approaches. So let me ask you a question. Who here in the room owns a LiDAR? Raise your hand. All right, a few of us. Who here owns an iPhone? Raise your hand. All right, a lot more. So it turns out if you have an iPhone 12 Pro or newer, you actually do own a LiDAR, which you're carrying around every day in your pocket. And these LiDAR sensors are becoming increasingly ubiquitous, not only on your iPhone, but also on virtual reality headsets and autonomous vehicles like Waymo. And while these LiDAR sensors are most often used to measure depth, providing point clouds like the one showed here, today I'll show you that their measurements can actually be used for much more. In particular, LiDARs are able to create and measure shadows. By illuminating different points in the scene with a laser, shadows are cast that reveal occluded or hidden geometry. And while RGB cameras can also measure shadows, these shadows become difficult to discern in high ambient light or when they mix together from multiple shadows. So instead, we use LiDAR, and in particular, multi-bounce light measured by the LiDAR allows us to overcome these challenges. So consider the scene shown here. We have a LiDAR sensor and a laser, and if we send a pulse of light into the scene, this light will scatter in all directions, including directly back to the sensor. And we refer to this light that scattered one time in the scene as first bounce light. And it codes the depth to every point in the scene that we directly illuminate. However, light doesn't just scatter one time in the scene. It continues to scatter multiple times and bounce around the scene. We refer to light that's scattered 2 times in the scene as two-bounce light, which looks like this. This two-bounce light actually shows us something magical, the propagation of scattered photons in space and time. And in addition, it also tells us information about shadows, thus allowing us to reason about hidden geometry. We model these multi-bounce light interactions using a recent advance in machine learning called neural rendering. By encoding or learning the geometry of a scene and the weights of a neural network, we're able to smoothly generate depth from novel viewpoints, as shown in our results here. But can we go even further? So far, we've discussed how we can reconstruct 3D scenes from a single view by scanning a laser over multiple points in the scene. However, in practice, today's consumer LiDARs typically illuminate multiple points in the scene simultaneously, meaning that all this light mixes together in each measurement. To overcome these challenges, we've developed the first of its kind large-scale multi-bounce LiDAR model that's able to unmix these measurements, enabling us to recover not only depth and hidden geometry, but also perform computer vision tasks like segmenting specular objects such as mirrors, which commonly cause failures in computer vision pipelines. We hope these advances could enable breakthroughs not only in robotics and autonomous driving and security as well, but also go beyond. So let me end with these questions. What would you do with the ability to see hidden objects? What use cases would this enable for your business? Thank you.
Thank you so much, Tzofi. If we could go back a slide just so we can leave his contact information up there, that would be great. How many years into your PhD are you?
I'm in my 4th year right now.
In your 4th year. So there's at least one more year, guys, to engage with Tzofi in this work. And I think one of the things that's really important here is to solicit that industry input, right, for the applications of this across industries. You know, we have a few ideas, but we really want yours. You mentioned neural rendering, and there's an interesting point of time right now that we're in with the acceleration not only of AI technology but of AI adoption. Mm-hmm. Could you speak to neural rendering and any other kind of recent advancements that are unlocks for this kind of work and what we could do?
Yeah, so neural rendering draws upon ideas from graphics and machine learning and allows you to take an analysis by synthesis approach, where given measurements, it could be RGB, but in our case, it's LiDAR, you learn the geometry of a scene such that you can then reconstruct those measurements in a completely self-supervised fashion. So rather than relying on training data, you're able to just take your raw measurements and use that to learn, in this case, the geometry of the scene by modeling kind of the interactions light would have with the scene.
So there's kind of a recency to this that has enabled this kind of work.
Exactly, right. Yeah. In particular, being able to make these pipelines differentiable allows us to apply kind of the latest, greatest machine learning toolery to it.
Right, right. And on a more personal level, you know, what motivates you and drives you? Why spend 5+ years of your life on this line of work? What was the initial driver and what drives you today?
Yeah, it's a great question. Before starting my PhD, I spent a couple of years working in industry, which I really enjoyed and learned a lot from.
Where?
And so I was at Lincoln Laboratory for 2.5 years, and then Amazon working on Alexa AI, which gave me great exposure. And coming here to MIT, I realized one of the differences is I was able to kind of explore this broad space of open problems. And what drew me to this problem in particular was the impact it could have across not just one sector, but multiple different sectors. Which I think is really exciting. And as we see these sensors becoming more and more ubiquitous, like I mentioned, I really see a potential for this technology to one day, hopefully in the near future, become more widely adopted.
Yeah, especially with the help of the people in this room.
Exactly.
Thank you so much.
Thank you.